Chemistry relies a lot on models, and models are very important because when we're talking about chemistry, we're talking about things at the atomic or molecular level, so things that are super teeny tiny that we cannot see with our naked eye. We can't even see it under a microscope. So we have to be able to model behavior of things that we just can't see. And one of the fundamental models that we use to describe the behavior of matter, which is kind of the name of the game for chemistry, is called Kinetic Molecular Theory. And the kinetic part tells you that we're talking about motion or movement. And the molecular part means of molecules or particles. Could also be at the atomic level, and we'll talk a little bit more about the distinction between molecules and atoms a little bit later on. And then this is just the theory that describes the movement and motion of these particles. So the original idea behind kinetic molecular theory is that everything is made up of tiny particles. Now, kinetic molecular theory came along before we had any concept of the atom. Not any concept of the atom, but just before we had a formalized concept of the atom. And so when we were talking about particles back in the day, we were talking about what are called corpuscles. That's what they called them. These little particles are called corpuscles. And all matter is made up of something that can be broken down further and further and further until you can't break it down anymore. Okay, so these tiny particles then have specific characteristics, and one of the characteristics, and this kind of speaks to this kinetic part of it, these particles are always in motion. So these things are always moving around. So even if I'm stationary, even if I have this pen and it's sitting there on the table, it is still in motion. The particles or the corpuscles or the atoms or the molecules within this pen are still moving around, always. And so we can't see that. We don't perceive it from the level that we're at, which is such a large macro scale comparatively. But these particles are always in motion, and that's an important feature to why they can do chemistry and why they can interact. Okay. The other thing about kinetic molecular theory is that it says that the particles are always in motion and there's a direct relationship between this motion and temperature. So a direct relationship means that if you change one thing about a system, so for instance, if I increase the temperature, I'm just going to put T for temperature there, then whatever it is that I'm comparing in that system, whatever other characteristic I'm looking at, if it also goes up, then that's a direct relationship. So when I increase the temperature, I increase the motion or the speed of the particles. And that's a direct relationship. If, as I changed one of the variables, the other one did the opposite, so if I increased one, if the other one went down, then that would be what is called an inverse relationship. But this is a direct relationship between motion and temperature, and that's pretty intuitive. We know that when we heat things up, we speed things up, right? And we've seen that in a lot of different ways. We know that metal, for example, when you heat it up, expands, right? Water moves around more when you heat it up, and it spreads out a little bit more because we're moving it around. Okay. The fourth thing that comes out of kinetic molecular theory is about the different phases of matter, states of matter. And it says that how free these particles are to move around, so this is related to the motion of these particles, how free they are to move around impacts what phase of matter they're in. phase of matter, or these are also called states of matter. Okay, so phase or state. And so the more free the particles are to move around, then the more free the phase of matter will be. And we're going to talk about that right now. So the different phases of matter, or the different states of matter that we talk about, are usually solids, liquids, and gases. And again, the reason that we care about matter is because chemistry is the study of matter. So we want to know everything about the structure and the behavior of matter. And so the phase of matter is important. So we talk about solids, liquids, and gases. So let's start with solids. Now we said we can define these phases of matter based on how free the particles are to move around. So a solid, you can maybe intuit that there's not a lot of freedom of motion. And actually in solids, things that are solid in terms of their phase of matter, we talk about their particles vibrating, not really zinging around in space. And these particles, then they're not very free to move around, and they're really closely packed together. So we could say that solids are pretty dense because that's kind of how close together the particles are, closely packed together. And if we're visualizing a solid, then it's usually a repeating array, and I'm just going to use these particles here as circles. So we have this repeating array of circles. They're all pretty tightly packed together. They can't move around very much. One of these particles here is going to be trapped by all of the particles around it. So if I'm looking at just this particle right here, then it has all of these particles that are surrounding it, which allow it to not be able to move, so not very free. So it kind of allows them to keep the form that they're in. And the way that we actually define solids is we say that they have a definite shape, or a constant shape, and a definite volume. So they always are going to be the same shape. This is the shape of my pen. It's not going to change. It's a solid, right? And a definite volume means it will always take up the same amount of space. So constant shape, constant volume is the way that we define solids. And because of that constant shape and constant volume, these particles are not very free to move around, or vice versa. You can think about it in the other way. Because the particles are not very free to move around, then they allow for this to be a definite shape and a definite volume. So they kind of feed into each other, this model. Now if we increase the degree of freedom here, meaning that these particles are able to move around a little bit more, then we come to the next phase of matter, which are liquids. So liquids are a little more free to move around, and in fact the particles of liquids can move past each other. So if I had a, let's say I have a flask here of liquid, there's my flask, there's liquid in it. I'm going to magnify this with my super magnifier and look at my individual liquid particles. Then I have these particles, and these are my motion lines. They're moving around within this sample. Because of kinetic molecular theory, it says that we're always in motion. So these things are all moving around. There's a little more space between them, you'll note, than there was for our others. So we have these particles that are always in motion. They're kind of moving around. This one can be moving past this other one. This one's going to move past this guy. This one's going to move past this guy, etc. So these particles can move around each other. They're not caged in like we saw with our solid. And this allows for liquid to flow, right? So we talk about the fluidity of a liquid, and we also will call liquids fluids. So that fluid movement or that flow comes about because the particles can move past each other. Okay, so liquids are a little more tightly packed than, say, a gas. Well, a lot more tightly packed than a gas, but definitely have a little more freedom to move around than solids. Okay, so that's kind of the difference between our two phases there. Now, if we increase the speed and the motion of these particles, oh, I forgot to talk about the shape and the volume. So we said that the solids have a definite shape and a definite volume. Liquids can take the shape of whatever container they're in. So if I put a liquid in this flask, it's going to take the shape of the flask. If I pour the liquid onto the ground, it's going to take the shape of a puddle. So they don't necessarily have a constant shape. So we say that they have an indefinite shape or a variable shape, and a definite volume, because it's still going to take up the same amount of space, whether it's in the shape of a flask or a shape of a puddle. It's still going to take up the same amount of room, so it still has a definite volume. Or another way to say that is we can't easily compress it. So when we push and we apply some pressure to it, then we can't easily expand or contract it, right? So a liquid's going to stay basically a liquid. Solids will definitely stay solids. All right, so now we increase our degree of freedom and we get to gases, which are our third phase or state of matter. Now, just as a side note here, there are other states of matter. There are other phases of matter that we've identified. One of them is plasmas, for instance. But we usually just focus on solids, liquids, and gases, at least at an introductory level, because they kind of provide the good models that we use to talk about matter in general. So gases have much more freedom to move around. So they're very free to move. The particles are very tiny. So no matter what gas it is, it has pretty small particles, so that's very free. Sorry that's kind of a mess. Very free to move around and very tiny particles. There's also then, because of this, lots of space between them. So if I have a container of gas, let's give myself another flask here. And if within this flask, I'm going to stopper it to make sure that all my gas stays in there. So here's my flask. Inside my flask, if I have a gas in there, then I'm looking at my gas particles, and here's my magnifier again. Then I have these teeny tiny particles that are in there, and they're zipping around, and there's lots of space, and there's not a lot of them in a given area. Okay, so they're very teeny tiny, very spread out, lots of space between them, and they're very fast moving. And that kind of goes back to our kinetic molecular theory that says that if we increase the temperature, we increase the speed and the motion of the particles. And so if we increase the speed and the motion of the particles, then we end up with a phase that is very free to move around, and that would be the gas phase. Now, unlike water or liquids in general and solids, when you try to compress a gas, it's much easier to compress a gas. We say that it is compressible, meaning that I can fit a certain number of gas particles in either a really small space or a really large space. And the reason for that is because there's so much space between the particles themselves. So that allows for this compressibility. And this is part of the reason that we can put gas in tanks, for instance. So we're scuba diving and we need a source of oxygen when we're down scuba diving. We can put a lot of oxygen in a really small amount of space because we've compressed it down. There's a lot of space between the particles, so there's a lot of room to push them together. And we'll talk about the properties that kind of shake out from all of this when we talk about the gas laws in a later video. But going back to the way that we've been defining these different phases of matter, we talked about them in terms of their shape and their volume. For gases, they have a variable shape and volume, or an indefinite shape and volume. So indefinite shape or variable shape, just like a liquid, it's going to take the shape of whatever container it's in. So my gas is in the shape of a flask, my gas is in the shape of a scuba tank, etc. It also has an indefinite volume, and that comes from this compressibility. I can squeeze it down into a smaller space, right? Or I can expand it out so that it fills a whole room, right? The same amount of gas can fill an entire room or fit into this flask because it has such tiny particles and there's so much room for them to move around. Okay, so variable shape, variable volume, or indefinite shape, indefinite volume, and that's our gases. Okay, so that's kinetic molecular theory. That's our different phases of matter. And we'll kind of talk about how this relates to the beginnings of chemistry in the following videos. So if you have any questions on this, don't hesitate to ask, and I'll talk to you again soon.